Right. In this presentation, I will be covering my postdoctoral research work in University of Missouri, followed by my high power microwave work in MTRDC, that is DRDO, and then master's research work in the IIT Kharagpur. The objective of this project is to make a compact high voltage X-ray source that can supply up to 160 kilovolts peak and with a variable current of 20 to 70 milliamperes. The important features in this X-ray generators is that it has to be made as compact as possible by using the advances in dielectrics materials, field emission cathode, and by eliminating the water cooling system and uh, other advances such as instead of the conventional transformer, we'll use the piezoelectric transformer. The block diagram shows that a driver circuit is connected to a high voltage piezoelectric transformer, which can step up the power watt. The output AC voltage is connected to a Coulomb multiplier, which can step up the AC voltage to a higher DC voltage. Driver circuit is inbuilt circuit for controlling piezoelectric transformer. And so the Coulomb generator is also built within the laboratory. This Coulomb generator is uh, optimized for 5 stages, which can produce up to 70 kilovolts, 70 kilovolts, and then once we have tested this circuit, uh, we uh, we built on a printed circuit board for testing in a transformer oil. Once we pass this circuit test, we can use epoxy resin to make it as a brick kind of circuit. The number of stages that we have used in copper watt is 5 stages, which can reaching up to 70 kilovolts. The piezoelectric transformer that is used is uh, lead zirconate titanate, and the advances in anode and cathode materials such as carbon nanotube cathodes were used in this project. So this is the full bridge driver circuit that drives the input frequency and the voltage given to the high voltage piezoelectric transformer. Here we have used four uh, MOSFET transistors, which is made of IRFP 4550. The gate of this four transistors M1, M2, M3, M4 are controlled by using the gate driver circuit, the gate drivers chip by using IR2110 by using the TL494 pulse width modulator. Here, the output of this high voltage piezoelectric transformer is controlled by uh, the input frequency by controlling the gate driver circuit. So the next project is from my scientist experience in DRDO in microwave tube development research development center in Bangalore. I have worked on pulse power supplies for the high power microwave generation. Specifically, I worked on testing this high voltage power supply with the Kali 200, Kali 1000, and Kali 500 series. Which the voltage ratings are 300, 600, 300, 300, and 600. The power ratings vary according to the current uh, it can it can supply, and the pulse width of the order of 50 to 100 nanoseconds to 80 to 100 nanoseconds. So this is a collaborative project that transfer the technology from the Baba Atomic Research Center to the DRDO laboratory. By working on this project, we have developed our own pulse forming line, and then a virtual cathode oscillator, which can convert this high compressed pulse to a very narrow radiative microwave frequency or radiative pulse. So here is a pulse power supply for HVM generation that we have designed in our laboratory for the voltages of 500 kilovolts, 10 kiloamperes, and 80 nanoseconds. The line that you can see here is a uh, a transmission line uh, which we use uh, so here is the pulse forming line, which will compress the input voltage from the box generator to a higher power with a lower time. As you can see that the pulse forming line is designed for 500 kilovolts, 10 kiloamperes. The parameters that we have designed is inner diameter of 72 and the outer diameter of 72 mm and the inner diameter of inner radius of 25 mm with a length of 200 centimeters. The inductance and capacitance values and the characteristic impedance is shown here at 28 ohms, and the insulating material is used as castor oil. Once we have built this circuit, designed and built this pulse forming line, the power supply is given by using a separately built max generator, max power supply, which will be supplied from one end, and then the other end, as you can see here, this is a virtual cathode oscillator. Here, a virtual cathode oscillator is connected, which will convert this pulse into a microwave and radiate to this end. And there is for this virtual cathode oscillator, it needs a high vacuum, which you can see an ion pump is connected. This is supplied by the power supply of a box generator. The next one is my master's thesis work that I have done in IIT Kharagpur. It is essentially the pulsed electric field application for the nanomaterials, in which I have developed high current and high voltage generators for the densification of nanomaterials. In this, we have used two different techniques for the nanomaterial compaction, that is spark plasma sintering and electro discharge compaction. In the spark plasma sintering technique, it is used that uh, uh, a rectangular current pulse generator having a very high amplitude in the range of 400 to 700 amperes is inbuilt with a pulse width of 30 milliseconds in the laboratory. There is a second method which I can use a rectified current pulse generator. In this, a simultaneous application of low voltage high current pulse with a uniaxial pressure is needs to be applied. The second method is electro discharge compaction, in which a high voltage short duration pulses are used for uh, uh, and in this the discharge period is of the order of hundreds of microseconds at a high voltage of 1 to 10 kilovolts. In this, these two high voltage and high current generators are developed in the laboratory. The following slides we will be discussing. The first one is a rectangular current pulse generator for spark plasma sintering. In this, we have used a six-stage uh, uh, capacitive inductive circuit to simulate a rectangular pulse. And we have varied by using a MATLAB simulations different parameters for getting a optimal output parameters. I'll show one of the example in the next slide. We have varied capacitance variation and inductance variation, charging distance, and numerous number of sections and the charging voltage variation. Uh, the magnitude of the rectangular current pulse amplitude is V by 2Z. Here you can see the one of the variation that we have done is the number of sections. By varying the number of sections from 10 sections to 5 sections, you can see that the pulse width is reduced from 54 milliseconds to 32 milliseconds. So from this, we have optimized and built a rectangular current pulse generator with 6 sections as shown in the laboratory. We have existing capacitor values that is of 25 nanofarads with a withstanding voltage of 60 volts, 60 kilovolts. We have inbuilt our own inductors with air core type, wire gauge of 21 diameter, and the characteristic impedance of this transmission line is of the order of 200 ohms. And as you can see, the uh, output of this current pulse as shown here. The uh, We have to match the characteristic impedance so that we will not see any reflections at the output end. So we have used 180 ohms carrying current carrying rheostat for use in the laboratory. Of the equipment that we have used. These are the waveforms that we have recorded by using this method, which we can apply um, for the samples for nanomaterial compaction. The next method that we have developed is high voltage generator, that is also called impulse voltage generation. As you can see here, the uh, power supply is stepped up to by using the auto transformer and a test transformer, you can step up into 10 kV from 230 volts. And we have used the AC to DC rectifier. And then that DC voltage is charged to a 25 nanofarad capacitor. We have discharged as a single pulse onto a potential divider, which will have a potential divider circuit is uh, made with the R1 uh, loading capacitor, and then R2, and then there is a material sample is connected here. By varying the uh, by uh, by varying this R1 and CL, we can vary the wavefront time, that is the rising time of the impulse voltage. And similarly, wave tail time is computed from the uh, generator capacitor and the loading capacitor. And this circuit is designed for 10 by 500 microseconds impulse voltage. We have existing generating capacity of 25 nanofarad. We have computed other nearest or computed other resistors and capacitors, and then employed the nearby values of those resistors and capacitors. Here you can see our build circuit, and that is used for the samples testing. There is a sample holder. The the output voltages uh, from this impulse voltage generator is shown here. We have used a, mm, a, a voltage divider to measure the output voltage at the uh, sample site.